Yes, we can see your screen. And
So you can hear me as well, right?
yes, so please go ahead. Thank you.
Okay. Yeah, thank you for the invitation and having me here. So I'll be talking about an EFT compendium for discoveries. So this talk is basically to understand how we can use effective field theory, to pin down the correct nature of physics, which is often certainly the beyond the standard model, and that we are trying to address through this series of papers. So I'll be using the glimpse of some of the results from this series of papers that we have written recently. So first, I would like to discuss two different approaches to effective field theory, bottom up and top down, which is pretty well known to the community. But this will certainly set the stage for me to fulfill the aim of the discussion. And then I'll be talking about that how this BSM's different kind of BSM theories we can realize in terms of an effective theory, and then of course to connect how these theoretical calculations and from the experimentalist point of view how they can match to the set of operators which actually affect different kind of observables, and we'll use them as a kind of a response screen, and then we'll adjudge that if you choose different kind of UV theories, how do they respond with respect to different kind of observables, and that will help us to discriminate different kind of models and their behaviors. And based on that, I will try to see that how do we classify the BSMs, the kind of a degeneracy and non-degeneracy in their effective operator space. And based on that discussions, I'll also briefly discuss like what will be the future directions, and if we observe some kind of new degrees of freedom or the new particles in recent future, and then how we can modify our known knowledge to pursue further. And then I'll conclude with the idea that we have floated recently, that from the experience point of view, if you get some kind of excess or some kind of you want to do some kind of focused analysis in a particular kind of operators. Now looking into that operator, if we ask the question that what kind of UV theories or what kind of heavy fields can lead to those kind of operators, how do you do that thing? So it's like looking to the operator and then constructing the heavy field, and so the BSM scenarios like a reverse engineering the thing. Well, so this is the bottom-up approach, and for example, what we do based on the symmetry at the low scale, and looking to the available infrared degrees of freedom, we write down the Lagrangian, and then the universal part we write down, and then based on the symmetry and looking at the invariance and so on, what we try to do, we try to capture the footprints of the unknown theory, which has been integrated out. Right, and that's what we include different kind of invariant independent basis of the effective operators. So these are the set of effective operators. Lambda is the cutoff, qi are the operators, and c is the corresponding Wilson coefficients. So here actually interestingly we add those operators from the symmetry point of view, and the exact nature of the new physics is not known to us. So we try to get the idea from different kind of fittings and all those things like we do for the SMEFT kind of analysis, that what could be the possible UV theory which is yet to be unveiled. And here the Wilson coefficient like a free parameter, so we do not know really how these Wilson coefficients are related to the different kind of parameter dependence of the UV theory. So they are, so in that sense, when you add these operators and their corresponding Wilson coefficients, there is no correlations among them. So they are treated to be independent. But on the other side, if we think about the top-down approach, where we start with some definite UV theory, and then what we do, if we look in some kind of standard model mediated standard model process, and that can be mediated by some kind of new physics. And on top of that, we have some pure new physics process as well, but we'll keep aside them. And then what we can do if the new physics scale is quite heavy and effective field theory can be validated, then we can integrate out that new physics fields or the heavy fields, and then we find that the similar kind of structure, the universal description from the standard model and some kind of effective operators. And now these effective operators capture the footprint of these nucleus interaction at the mass scales. So unlike the previous one, here these Wilson coefficients are actually function of these heavy fields and their masses and their couplings. So now you can see you can get lead to the same nucleus interactions can lead to different kind of operators. But now, unlike the previous one, here the Wilson coefficients actually may be the function of different Wilson coefficients are function of the similar kind of new physics interactions and the mass scale. So in that sense, from the parametric point of view, the operators could be independent, but the Wilson coefficients will be related to each other. And later in one example, we'll see that how this parametric dependence in the Wilson coefficient space that can matter for a bottom-up and the top-down approach. Okay, so now we have developed an automated tool which is based on the covariant data expansion. And what does it do is following. So it can calculate this complete one loop Wilson coefficients. So it's like a manually matching of the BSMs and the SMEFT is there. So what you can do, you can write down the Lagrangian in the particular mathematical format that we have set there, and then you can identify the heavy field, and then you can integrate out that heavy field. So you can calculate the tree-level Wilson coefficients and the effective operators, as well as you can go to one loop process as well. So once you calculate all these operators at the UV scale or the matching scale, then you can use this codec thing to calculate further, and then you can perform their running as well to the electric scale using this anomalous dimension matrix that Trot and those collaborators have developed. Using the help of this anomalous ADM matrices, we can run them down to the electric scale and find out the low scale Wilson coefficients as well. So here, this is the idea that we try to float that. Okay, so if you start with different kind of BSM theories, then how we can bring them in the same footing using the effective field theory. So let's see. Now this is the renormalizable Lagrangian of this infrared theories, and then we can use this program that we have developed, which is basically it will calculate the effective operators up to any dimensions, a group invariant polynomials it calculates. And then what you can do, you can calculate the complete set of independent operators at any given dimension. So this is from the bottom-up approach. For example, let's consider this is to be the SMEFT one, if the low energy theory is the standard model. And now you have different kind of UV theories which are developed for different kind of phenomenological reasons. For example, like neutrino bias or different kind of LHC related physics or dark matter or whatever. And then let's say you have for example, you can have different three UV theories, and then you identify and that okay, so what are the basically your UV fields or the heavy fields or the non-standard model fields, and then once you identify them, you can certainly integrate them out, and you'll be left out with the standard model divisor freedom, and then you'll find out that you'll get a subset of these operators, of this full complete set of effective operators, right? And then you can move into some different theories, and you can certainly identify what are the UV fields or the heavy fields, and you can certainly then integrate out. And similarly, you can continue doing that thing for all such your preferred UV theories. So now you can see at this level, their interactions and their field contents could be different. So it's very difficult to compare them. But what you can do, if you can reduce them in terms of this SMEFT basis, and then you'll get a subset of these effective operators, which will contain the information or the footprints of those heavy interactions and their mass scales. And so if you consider them to be those heavy fields to be degenerate more or less, then you can bring them in the same footing as the SMEFT. So now you can see that because the characteristics of these interactions in different UV theories are different, so that will lead to different set of operators. Now theory 1 and theory 2 may have certain kind of overlap, or similarly 2 and 3 may have certain kind of overlap, and so on. So once you identify that, okay, what are the common set of operators, then you would expect the observers related to those kind of operators will be common for all the theories. And then it will be difficult to pin down or discriminate this kind of models. But certainly what you can find out, it may be possible that you can get some kind of operators related to this kind of theory, which are basically absent in on the operator set that you are achieving from model 2 or model 3. Then if you can in principle design some kind of observables related to those specific operators, which will be the smoking gun features of those particular theory, and the observation or the non-observation of those kind of observations certainly may help you to classify the what kind of UV theories are being favored by the data or not. So this is the like one of the stepping stone to discriminate different kind of UV theories relying on this effective field theory approach. So yeah, so for that we can see that you need two tools. One will help you to bring down different kind of UV theories to the SMEFT level, or if you think about along with the SMEFT, if you want to add some lighter degrees of freedom, let's say right hand neutrino or some charge scalar and so on. If you want to extend the SMEFT basis based on the future discoveries, for that you need to include them using this our grid. And so one can have actually in a both way. You can pinch this kind of thing and try to find out that what kind of UV theories actually are degenerate from the effective point of view and what are not, and how to discriminate them and so on. So now I'll be emphasizing that how there's a correspondence of the observers and the effective things. So what you can parameterize this different kind of observers based on a set of some effective operators, and these are the nice references where they have written down which effective operators actually affect different kind of low energy observers. So for the example, here I'll be focusing on basically electric equation observers and the Higgs signal strength. So you can see at the leading order electric equation observers are affected by this set of operators, and then you might be wondering to see that okay, why did I differentiate this NL1 and NL2? It is just for the presentation point of view. So we have categorically these three operators are part of this NLO, and certainly also these operators well. But the Higgs signal strength actually contains these three such operators, not all those things. And on top of that, we have these operators. So now you can find out, okay, so you have different UV theories you consider, and then you bring them down at the electric scale, and then you find out the set of operators. Now you can see, looking into this set, you can really identify that how this operators set or the particular UV theory will respond to this kind of different kind of low energy observers. And on top of that, sometimes you get some additional operators which is named as add ops. So these are certainly not affecting these kind of observables, but they may be involved in different kind of observables if you can design. And on top of that, you may focus on this baryon number electron overheating operators, and which can lead to different kind of layer process as well. Fine. So now what we have done, so we have considered different kind of UV extensions through these heavy scalar fields. So we have classified them based on these two categories. One is color singlets, one is basically the color scalar. So you can see here we have defined these 15 different scenarios where we have starting with the singlet scalar, and then you have a W charge scalar, the real triplet, the Higgs doublet, and so on, that complex triplet and the quadruplet, and similarly different kind of leptoquarks motivate for different kind of phenomenological reasons. Now we have this, let's say for example, this 15 different scenarios, and looking into this, we find that okay, so how do we discriminate their impact in low energy observers? And to do so, what we have done actually, we analyze one of the each cases individually, and we assume that standard model is extended by one of the heavy scalar at a time, and we integrate them out up to one loop, and we generate this effective properties using this our program codec. So now, before going to that, let me tell you that what kind of operators will be talking about. So there will be some operators which will be generated through the T levels. So that we define by the T, where the heavy fields are appearing as a T level propagator. And then you can have a new physics theories which are coming in the loop. Now in the loop, all the propagators are heavy fields that we call the heavy loop or the HH. And then on top of that, you can have a loop standard particles as well as the heavy particles, and that we call the heavy light mixing. So this is the way of unfurling in the effective operators in terms of this diagrammatically. So now this is a quite busy slide, but going into much detail about this, what I'm trying to highlight in that, okay, you can see this 15 such models we are considering, and then we are showing for each model up to this one loop what are those operators you will be generating. So this is like electric equation observable at leading order. You can see that in a singlet, heavy singlet, you get only these two operators through this heavy light mixing, and then some operators will be generated at tree level, and so on. Similarly, you can see that there are some cross implies that these operators not being generated up to one loop even after considering the heavy light mixing. And so in this way, you can really classify them, and also they will lead to some other set of operators which will belong to this electric position observable in LO2. And on top of that, there are some additional operators as well as the DL violating operators as well. So you can see that a lot of operators are being generated at the loop level. So if you are restricting yourself up to T level, so I think you'll be missing out a lot of operators. Fine. So once we have this table, so we know that what are the operators set correspond to different kind of heavy field. So here from the EFT notion that one of the UV theory is represented by a set of operators, right? So now what we are doing that we try to understand that how these different kind of observers, which we define as a response screen, how they treat those different kind of models. So if you consider this electric position observable at leading order, and that screen will have this kind of structures, and then you starting with the 15 different models, and then you see that you will get 4 different classes. That implies that all these models offer the same set of operators which will affect your electric position observable at leading order. Similarly, class 2 contain different set of operators, and class 3 and class 4. So that means basically we have 4 non-degenerate classes, and each class may have the degeneracy from the point of there because they are sharing the same set of effective operators, right? And similarly, you can continue doing this thing with the, let's say, Higgs signal strength. There you will get 6 different non-degenerate classes, but each class may contain multiple degenerate scenarios. And then you can see, comparing your left and right screens, that the appearance of the degeneracy in the model space actually depend on the particular set of observables, right? And similarly, you can do with the NLO of thing for the electric position observables, and there you can classify them accordingly, and so on based on the additional operators. Now, what will happen if we include all these observables simultaneously? Then this is the picture that you are getting. That you start with these 15 different models, you pass them through different kind of observable set, and finally you can see that okay, that models are basically now non-degenerate, but still there are some classes like this second, third, and third, fourth, and fifth classes which contain multiple models. That means if you include only this set of observables, and also if you integrate out up to this one loop, then this delta 1 and sigma, they offer the same set of operators. Okay, so it's very difficult to discriminate them looking to their operator structure. And so true for the chi2, chi3, which are the different kind of leptoquarks, and theta1, theta2, chi1. But otherwise, the chi4, phi1, phi2, they are actually singled out. That means each of them actually contain at least one operator which is absent on the other, and that could be the smoking gun feature for that kind of particular model. Now, as I was telling, that there is some way of looking to the bottom up and top down. Now, from a model perspective, how to understand that thing? So you can see that here we are looking at the CHB versus CH box map plane, and see that okay, so you have this standard model extension by that doublet scalar, or a quadruplet, or a complex triplet, and once you integrate them out up to this one loop, then you will get only 9 operators. Okay, and from the bottom up approach, if you consider these 9 operators to be independent, and then you get this gray ellipse map after the fitting all these electric position observables and the Higgs signal strength. But once you know that all these models are basically at the UV scale, and then you integrate them out, then you know the Wilson coefficients are actually function of the model parameters. So instead of 9, though you find out these 9 operators, but those 9 operators will be dependent on these 3 parameters. So effectively the degrees of freedom is less, and that are basically the correlation, and that's basically tightly constant. Now you can see, so if you come down from the UV theory, then you cannot access you cannot satisfy all this gray region, rather you get a minuscule region out of that. And if you zoom in that thing, then you can see that still that the model interactions and those things are so different, but after fitting in all those things, they are very highly degenerate, and you need a very huge amount of data or the patient data to discriminate them further to crack their degeneracy. And similarly to for different kind of leptoquark scalar. So if you start with this theta 1, theta 2, omega, then you get, after them integrating out, 5 such operators. So you get these gray ellipse in this CHB versus CH box plane. But once you integrate them from the top down approach, they are basically function of one parameter. And then you can see there's a basically minuscule regime which will satisfy all this low energy data. And once you zoom in that thing, then you can see that how different kind of models have their dependence in the parameters space. And so the lesson is basically they're highly degenerate, and we need to really think about how to break their degeneracy and so on.
Hi,
So now,
Joydeep, you have 5 minutes left in total. Thank you.
Okay, thank you. Yeah. So now once we have this based on what we have observed so far, if we ask the question that in future, if we find out some new particles, then how to extend that idea? The idea basically you can extend that if you find out some singly charge or W charge, based on that you can extend the SMEFT basis, and which you call the BSM basis, certainly. Okay, and then similarly you can choose your set of theories which contain those newly observed singly charged or W charge particles or different kind of multiplets, and then you can play the same game, and then that will help you to discriminate different kind of UV theories. And for example, why these are important, like for example, if you consider like some kind of left symmetry model, and depending on their hierarchy of the spectrum, they can lead to different kind of extensions. So that's why we are focusing on this extended BSM basis, and based on the futuristic discovery prospect, and that could be important, looking beyond SMEFT basis. Yeah. So this is the last point I want to emphasize, that if you have an operator and if you have a set of operators in your mind, then how to construct a UV theory. So that we come up with this paper in the EFT Diagrammatica, that will try to give you the UV roots of CP conserving dimension 6 SMEFT operator. Now, for example, you start with like chi-square 5 cube class of operators. Okay, and this is the effective diagram for that. And what you can do, you can unfold without considering any kind of internal symmetry. You just look at the Lorentz invariant structures, and then you can unfold that in terms of single heavy fields or their interaction. And once you fix for a particular operator the external states, and that will uniquely give you what kind of heavy fields representation could be there. Like for example, QH can be generated through this scalar or the Fermionic representations, heavy representations. QUH can be generated and this thing, and so on. And similarly you can do for psi4 as well. So what we have done, actually we have classified all the dimension 6 SMEFT operator and unfold them in terms of the UV interactions, and we have cataloged them what kind of heavy fields can be there, and such that you get this operator, and also that will help you to build the new BSM scenarios looking into those kind of SMEFT operators and so on. Yeah. So now, so what is the take-home message? That as we can agree that our primary aim to pin down the correct nature of UV theory, and we find out that there should be some complementary analysis for the bottom-up and top-down approach are important to pin down those correct nature of physics. And here we need to find out different kind of observables, which are nothing but a set of effective operators to adjudge different kind of BSM theories, which are reduced in terms of their effective theories. And also we have developed this identification of heavy fields for different kind of individual SMEFT operators. It will be a good guideline for a further model building. And we have also emphasized how to extend our existing knowledge if a new particle is discovered, and then BSMT would direct to that thing. Okay, thank you.
Okay, thank you, Joydeep. Okay, so we have time for questions. Let's see if we have any from the room. And if there are any from the remote side. Okay, maybe I can ask a question on the on page 15 when you show the contours comparing the bottom-up approach and your BSM. So I think visually the contour from the bottom-up approach was much more loose, right, than the this BSM case. Was that like related to the data set, to the measurements you are using, like that do not give you constraints? Yeah, please.
Yeah, so the thing is basically, of course, once you incorporate more and more data, of course, I mean, you will squeeze this parameter space. But what I'm trying to emphasize that the difference between the parameter space when you approach bottom up, because you get 9 operators and 9 operators are independent. So your degrees of freedom is quite large. But when you come from the top bottom, you get the same 9 operators, but because these Wilson coefficients are function of model parameters, so though you have 9 operators, but they are function of 3. So the degrees of freedom is 3. So that's the difference actually. And in both cases, you are using the same set of data actually. So under the light of same set of data, the difference is basically in one bottom-up approach, you are having a 9 degrees of freedom fit, but in the top-down approach, you have 3 parameter fitting. So that's the reason of this constraint.
Right. So that's kind of related to statistical power of your data, right? Sorry, I still was not sure what are the measurements you used to compare these two scenarios. I mean, you must have used some sort of like electric pole precision observable or something like that, right? Yeah.
So we have included the electric precision observables and Higgs signal strength for this thing.
Okay.
So
and then sorry, and then you chosen to show the results on this two-dimensional place, right? Okay.
Yes. So where the other Wilson coefficients and parameters are marginalized.
Okay, thank you. So let me ask again if there are any questions from the room or from the Zoom. Okay, if not, then thank you again, Joydeep, for the very nice talk. And then I would like to also thank all the speakers in the morning session. We ran a little late, and I mean there was also limited time for questions. But I think from the organizers' point of view, we would like to recommend, especially the speakers, to look at your Slack channel. So we already have quite some interesting discussion happening there. And please take a look and iterate with others who are interested in your work. In that case, so I would like to close